Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the Booth multiplier and we will understand the Booth's algorithm for the serial multiplication. So in the previous video, we have seen that how to perform the binary multiplication using the add and shift method. And then after, we have seen the circuit for that as well as we have also seen the simulation. So we have seen that this binary multiplication using this add and shift method, we will require the 4 add as well as the 4 shift operations. Or in general we can say that for multiplying the two n-bit numbers, we will require the n arithmetic operations as well as the n shift operations. So typically, to perform the one arithmetic operation, it will require the one clock cycle. And similarly, the one clock cycle will be required for the shift operation. So for example, if we are multiplying the two 32-bit numbers, then we will require the 32 clock cycles for the arithmetic operations and the 32 clock cycles for the shift operation. Or in general, we will require the 64 clock cycles. That means as the n increases, then the required number of add and shift operations will also increase, and due to that, the required time for getting the result will also increase. But using some algorithms, it is possible to reduce the number of arithmetic operations during this multiplication. And one such algorithm is the Booth's algorithm for the serial multiplication. So in this video, through a couple of examples, we will understand that how this Booth's algorithm works, and using that, how we can reduce the execution time. So in the serial multiplication using this add and shift method, what we are doing, we are comparing the each bit of the multiplier at a time. So if that bit is 0, then we are adding the 0 to the accumulator, and if that is the 1, then we are adding the multiplicand to the accumulator. And after that, we are performing the right shift operation. But in the Booth's algorithm, instead of comparing the single bit, we will compare the two bits at a time, that is q0 and the q minus 1. So here, first we will compare these two bits, and then in the next iteration, we will compare the q0 with the q1. And later on, we will compare this q1 with the q2. And based on these two bits, we will perform either add, subtract or the shift operation. So initially, when the multiplication process starts, at that time, this q minus 1 bit will be set to 0. And based on this q0 and the q minus 1 bits, the multiplicand is either added or subtracted from the accumulator. And initially, this accumulator or this A register is also set to 0. So here, if this q0 and the q minus 1 are 0 0 or the 1 1, then the no addition will be performed. And in that case, directly we will perform the shift operation. On the other hand, if this q0 and the q minus 1 are 0 1, then the A plus M will be performed, and the result will be once again stored in this A register. On the other hand, if this q0 and the q minus 1 bits are 1 0, in that case, this subtraction will be performed. And after this addition or the subtraction, we will have this right shift operation. So here, this right shift operation will be the arithmetic right shift operation. While if you see the earlier case, then in this earlier case of add and shift method, we were doing the logical shift operation. And in this way, after the each right shift operation, the next pair of bits in the multiplier will be checked. So in this method, whenever there is a multiple ones or zeros in the multiplier, then there is no need to perform the arithmetic operation. And in this way, we can reduce the required time for the multiplication. Now another advantage of this Booth's algorithm is that it also works for the signed numbers. That means using this algorithm, we can also multiply the signed numbers, and at the same time, we can reduce the execution time. So now using this algorithm, let us see how to multiply the two signed numbers. So here, these signed numbers are represented in the 2's complement form. So here, this 1010 corresponds to minus 6, while this 0101 corresponds to 5. And we know that when we multiply the minus 6 and the 5, then the result will be equal to minus 30. And in the 2's complement form, it can be represented like this. So like I said, when the multiplication process starts, at that time initially this accumulator and this q minus 1 bit will be set to 0. And then after, this multiplicand and the multipliers will be loaded in this M and the Q registers respectively. And after that, the multiplication process will start. So let us understand how this Booth's multiplication algorithm will work. So here, like I said, this q is equal to 1010 while the multiplicand is equal to 0101, and this should be the answer, right? Now during this multiplication process, depending on the q0 and the q minus 1 bit, we might perform the addition or the subtraction. That means during the multiplication process, we also require the subtraction, that is equal to a minus m. And we know that this a minus m is equivalent of adding the a with the 2's complement of the m. So let's say the 2's complement of the m is equal to m bar, and here that will be equal to 1011. That means the a minus m is equivalent of a plus m bar. That means here during the multiplication process, wherever we need to perform the a minus m, at that time we will perform this a plus m bar. So here, since we are performing the 4-bit multiplication, so this accumulator and this q registers will be of the 4 bits. And initially, this a and the q minus 1 will be set to 0. So in the first iteration, this q minus 1 and the q0 bits will be checked. And here, since they are 0, so no arithmetic operation will be performed. And directly, we will perform the arithmetic right shift operation. So as you know, in the arithmetic right shift operation, the MSB will be copied as it is, and after that, all the bits will be shifted to the right side by a 1-bit position. So now, after the first right shift operation, once again, this q0 and the q minus 1 bits will be checked. So now if you see, then that is equal to 10. That means now the subtraction will be performed, and that is equal to a plus m bar. That means now the m bar will be added with the current value of the a register. So after the addition, we will get this 1011, and here this q and the q minus 1 will be copied as it is. So after this addition, or in a way, after this subtraction, once again the right shift operation will be performed. So after this arithmetic right shift operation, this will be the content of this aq as well as the q minus 1. So far, only 2 times this q0 and the q minus 1 bits have been checked. But here, since it is a 4-bit multiplication, so this process will be repeated 2 more times. So now, if we check the q0 and the q minus 1 bits for the 3rd time, then that is equal to 01. So now, the a plus m will be performed. That means now, this multiplicand will be added with the current value of the a register. And after the addition, this will be the value of the a register. So here, during the addition, if there is any carry generated, then that will be neglected. So here if you see, then this 1 plus 1 is equal to 0, and there will be a carry of the 1. So this 1 will come over here, and then if we move to the next column, then once again, here this 1 plus 1 is equal to 0, and there will be a carry of the 1. So once again, this 1 plus 1 is 0, and there will be a carry of the 1. So here, this carry will be neglected. So we can say that this will be the content of the a register. And here, this q and the q minus 1 will remain as it is. So here, after this addition, once again, the arithmetic right shift operation will be performed. And after that, this will be the content of the aq as well as the q minus 1. So after this 3rd right shift operation, once again, this q0 and the q minus 1 bits will be checked. And now if you see, then that is equal to 10. That means once again, the a minus m will be performed. Or in other words, this m bar will be added with the current value of the a register. So after the addition if we see, then the value of the a will be equal to 1100. And during the addition, if there is any carry, then that will be neglected. And once again, here the content of the q and the q minus 1 will remain as it is. So after the addition, once again, the right shift operation will be performed. And after the arithmetic right shift operation, this will be the content of the aq and the q minus 1. So here, the content of the a and the q will represent the final output. That is equal to 1110, 0010. And in the 2's complement form, that is equivalent to minus 30. So as you can see, in this Booth's algorithm, in the each iteration, this q0 and the q minus 1 will be compared. And based on that, either addition, subtraction or no arithmetic operation will be performed. And after checking that, the arithmetic right shift operation will be performed. So here, whenever there is a consecutive zeros or the ones in the multiplier, at that time, we can avoid the arithmetic right shift operation. And in this way, it is possible to perform the multiplication process little faster. So for a better understanding, let us take couple of more examples. So in the second example, if we see the multiplier, then that is equal to 0, 1, 1, 1 and the multiplicand is equal to 1, 0, 0, 1. That means if we see the value of the q, then that is equal to 7 while the multiplicand is equal to minus 7 and the answer will be equal to minus 49 or in the 2's complement form that is equal to 1, 1, 0, 0, 1, 1, 1, 1. So as you can see in the multiplier, since we have a consecutive ones, so as per this Booth's algorithm, the required number of arithmetic operations will be less. So once again, during this multiplication process, since we might require the subtraction, so let us also find the m bar, that is the 2's complement of the m, and in this case, that will be equal to 0, 1, 1, 1. So once again, here since we are performing the 4-bit multiplication, so the length of the A and the Q registers will be of the 4 bits. And if we see the final partial product, then it will be of the 8 bits. So initially, this A and the Q minus 1 will be set to 0. And now, the bits Q0 and the Q minus 1 will be checked. So here, since they are 1, 0, so the subtraction will be performed. That is equal to A minus M. Or equivalently, the M bar will be added with the current value of the A register. So after the addition, the content of the A register will be equal to 0, 1, 1, 1. And here, the Q and the Q minus 1 will remain as it is. So after the addition, the first arithmetic right shift operation will be performed. That means here, the MSB will be kept as it is. And after that, all the bits will be right shifted by the 1 bit position. So after the first right shift operation, if we see the content of the Q0 and the Q minus 1, then that is equal to 1, 1. That means here, no arithmetic operations will be performed and directly we will perform the arithmetic right shift operation. That means now, after the arithmetic right shift operation, this will be the new content of the AQ and the Q minus 1. And once again, now this Q0 and the Q minus 1 bits will be compared. So once again, since they are 1, 1, so no arithmetic operation will be performed and directly we will perform the right shift operation. So after the third arithmetic right shift operation, this will be the content of the AQ and the Q minus 1. And now, last time, this Q0 and the Q minus 1 bits will be compared. So now if you see, then they are 0, 1. That means now, the multiplicand will be added with the current value of the A register. And after the addition, this will be the value of the A register. That is equal to 1, 0, 0, 1. And here, the content of the Q and the Q minus 1 will remain as it is. And after this addition, once again, the final arithmetic right shift operation will be performed. So after this arithmetic right shift operation, this will be the content of the AQ and the Q minus 1. And here, the content of this A and the Q register will represent the final output. That is equal to 1, 1, 0, 0, 1, 1, 1, 1. Or in the 2's complement form, that is equal to minus 49. So as you can see, in this case, we have performed the 4 shift operations and we have performed only 2 arithmetic operations. And in this way, we can reduce the processing time. So now, let us quickly see the third example, where both multiplier and the multiplicand are positive. So here, the multiplier is equal to 0, 1, 1, 0 and the multiplicand is also equal to 0, 1, 1, 0 or in the decimal that is equal to 6. So after the multiplication, the answer should be equal to 36 or in the 2's complement form that is equal to 0, 1, 1, 0, 0, 1, 0, 0. So once again, since we might require the m bar, so for that, let us also find the 2's complement of the m. So here, the 2's complement of the m is equal to 1, 0, 1, 0. And now, let us start the multiplication process. So here, first this a and the q minus 1 will be set to 0. And first, this q0 and the q minus 1 bits will be checked. So here, since they are 0, so no arithmetic operation will be performed. And directly, we will perform the arithmetic right shift operation. So after the first arithmetic right shift operation, this will be the content of the a, q and the q minus 1. And now, once again after the shift operation, this q0 and the q minus 1 bits will be checked. So at the second time if we see, then that is equal to 1 0. And since they are 1 0, so now this a minus m will be performed. That is equivalent of adding the m bar with the current value of the a register. So after the addition, the new value of the a register will be equal to 1 0 1 0. And here the q and the q minus 1 will remain as it is. So after this addition, once again, this arithmetic right shift operation will be performed. And after this right shift operation, this will be the content of the a, q and the q minus 1. So here, the second right shift operation will complete the second iteration. And now, for the third iteration, once again, this q0 and the q minus 1 bits will be checked. So since they are 1 1, so in this third iteration, no addition will be performed. And directly, we will perform the right shift operation. So after the third arithmetic right shift operation, this will be the content of the a, q and the q minus 1. So in this way, the three iterations have been completed. And now for the fourth iteration, once again, this q0 and the q minus 1 bits will be checked. So now if you see, then that is equal to 0 1. And therefore, now the addition will be performed. That means now, this multiplicand will be added with the current value of the a register. So after the addition, this will be the content of the a register. And during the addition, if any carry is generated, then that will be neglected. And at the same time, the content of the q and the q minus 1 will remain as it is. So after the addition, once again, now the arithmetic right shift operation will be performed. That means here, the MSB will be copied as it is. And now, all the bits will be right shifted by the 1 bit position. So here, this fourth right shift operation will complete the fourth iteration. And after this fourth iteration, the content of the A and the Q register represents the final output, that is equal to 0010 0100, and in the 2's complement form, that is equal to 36. So in this way, using this Booth's algorithm, it is possible to perform the multiplication of the signed numbers. So as we have seen in this Booth's algorithm, for the n-bit multiplication, we are going through the n iterations, and in the each iteration, we are checking this q0 and the q minus 1 bits. And based on these two bits, we are deciding whether the arithmetic operation will be required or not. And after that, we are performing the arithmetic right shift operation. That means here, as per this Booth's algorithm, while multiplying the two n-bit numbers, we will require the n shift operations, and the required number of arithmetic operation will depend on the value of the q0 and the q minus 1 bits. Or basically, it will depend on the pattern of the multiplier bits. So in the multiplier, if there is a pattern of consecutive ones or zeros, then as per this Booth's algorithm, it is possible to reduce the number of arithmetic operations. So that is the basic algorithm of the Booth's multiplier. So now, let us see the basic block diagram of the Booth's multiplier, and let us briefly understand how it can be implemented in the hardware. So this is the basic block diagram of the Booth's multiplier. So here, for the multiplication, we will require the 3 n-bit registers, that is A, Q and the M, where the A is the accumulator and this Q stores the multiplier, and similarly, this M register will store the multiplicand. So apart from that, there will be a circuit which will perform the 2's complement of the multiplicand, and that M bar will be stored in the another register. So now, to perform this addition, here we will also have the arithmetic circuit. So here, based on this q0 and the q minus 1 bits, this control circuit will decide whether we need to perform the addition or the subtraction, and accordingly, it will generate the selection input for the multiplier. That means if the M bar is selected, then the subtraction will be performed, and if this M is selected, then the addition will be performed. And after the addition, the result will be stored back in this A register. And once this arithmetic operation is over, then the shift operation will be performed. So to perform this shift operation, this control unit will generate the command signal. So here, while checking this Q0 and the Q-1 bits, if these two bits are either 00 or the 11, in that case, this control circuit will directly generate the control signal for the right shift operation. And at the same time, this control unit will also count the number of iterations. So that is the basic block diagram of the Booth's multiplier. So typically, in the embedded hardware, like in the FPGA, this multiplier circuit can be implemented easily. But probably in the upcoming videos, we will see that how the same can also be implemented using the discrete hardware. And I will also show you the simulation result for that implementation. But I hope in this video you understood how the Booth's algorithm works and what are the advantages of this Booth's algorithm over the conventional add and shift method for the multiplication. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.